Hi everybody, and welcome to our final lecture on regression and of the summer semester. Congratulations for making it this far. The finish line is in sight. You just have to hand in your final project, and it looks like everybody's on track to get a good grade, assuming the final project goes well. So the last topic I wanted to talk about is definitely the most important in terms of regression, and arguably the most important of this class, which is checking the validity of our model. So we talked about how to build a regression model. Statistical software makes it very easy. We talked about the interpretation of coefficients, significance, and how we're testing the hypothesis of the relationship between the variables more thoroughly than with a correlation coefficient. I shouldn't say more thoroughly, but more objectively, because you can get a p-value out of it, whereas a regression coefficient is somewhat subjective as far as what's strong, and it does vary based on what you're studying. Like I know we covered the general rule that a regression coefficient of 0.7 and above is strong, somewhere between 0.3 and 0.7 is moderate, less than 0.3 is weak. But that's kind of a rule of thumb. Depending on what you're studying, 0.3 could be strong. So with regression, we can more accurately measure we can more specifically test the significance of the relationship between our variables by looking at the p-value associated with the coefficient for that variable. So that's a summary of what we've been doing and some of the benefits. Now I want to talk about validity. So there's a handful of assumptions you should be aware of, and they all are derived, or at least there's several ways to check assumptions, but I'm going to teach you how to check them using the residual plot to limit the amount of tools you have to learn, and I think you can test most assumptions pretty accurately here. That said, it is a little more subjective than some of the other statistical tests to test assumptions, which result in a p-value that's more objective and interpretable than looking at a residual plot. So this is an example of a residual plot from a regression line, and I want to go over what it means before we get into assumptions. So residuals, you might remember, are sometimes called errors. I like to think of them as errors. It's the difference between what you predicted and your actual data point for each data point. On the x-axis, you have your fitted values, meaning your predicted values, and on your y-axis, you have the residual for that fitted value. So intuitively, you can, and this is a little bit of a foreshadowing into the assumptions, you can think about how a pattern here might be in violation of certain assumptions related to regression. What I mean by that is that if your predicted values have low residuals during a certain region but higher residuals outside of that in another region, maybe your assumption of linearity is violated. And in this particular regression plot, sorry, I jumped around. In this particular regression plot, we're looking at residuals that are behaving as expected. No assumptions were violated. And there's a few ways I know that, but one of them is that they're kind of evenly scattered, and it takes some practice to get good at doing this. The more residual plots you look at and the more tests of your assumptions you do, the better you'll be able to identify this, but they're pretty randomly scattered over the full range of fitted values, right? So you want them to be centered around 0, because that's the assumption about our error, is that they're centered at 0, and you want them to be kind of even in their variation throughout all your fitted values. So this is a pretty good residual plot. Even with a low sample size, we see that they are centered at 0 and pretty even over the full range of fitted values. Now let's go into more detail about what those assumptions are. And this is just a handy little mnemonic to mention the assumptions related by or related to your model in specific, in particular. So the first one is linearity. This is a pretty obvious assumption of regression, right? We're fitting a straight line through our data in multi-dimensional dimensions, a plane, and so forth. But this assumes that the effect of your variable is constant over the full range of that variable's values and other variables in the case of multivariate regression, which is not always accurate. And there are ways to fix that with transformations, but we're not going to cover that in this course. I just want you to be aware you are assuming linearity. And that's kind of what I was getting at when I said in the event your model has a lower range of residuals in a certain area and then a higher range in another area, it's likely the case that your model isn't linear. And that also relates to another assumption we'll talk about later called equal or constant variance. But I do like this mnemonic line, so we're going to refer to it as equal variance because it fits the mnemonic better. So the first assumption we talked about is linearity. The next is independence. This just means there's no pattern in the residuals, so the value of previous residuals doesn't affect the value of future residuals, right? They're all randomly drawn across the line. So if we go back to our regression model, it's not like here we have a higher than we've seen previously residual, so the residuals continue to grow in value, right? They're all kind of come from this draw from a normal distribution that's centered at 0, and the spacing doesn't vary based on the prior observations. So that's the idea behind independence. I know that one's a little vague, but we're going to go through some examples, so don't worry. Normality is what I was talking about earlier. It's the distribution of the residuals. So if you think about the normal distribution, there's a lot of mass around the middle, and we're assuming they're centered at 0, which is what this notation is telling us. So there's a lot of mass around 0, and then getting further and further away has less probability. So that's the assumption of normality. And then the last assumption is constant variance, which is related to what I was saying before, as far as you want your variables to be dispersed evenly throughout the full range of fitted values, or the full range of your data, not necessarily fitted values. So these last three assumptions, the I, N, and E, independence, normality, and equal variance, can really be summarized by this one singular statement that you'll see repeated over and over again when people are listing the assumptions they make in their regression model. It's that your errors are distributed IID. IID stands for identically, independent, and identically distributed. From a normal distribution, that's what the N means, centered at 0, with a constant variance. And sometimes you'll see people write sigma squared to symbolize the variance. I wrote a C just to make it clear that it's constant, it's not changing. You could write it any way as long as you're clear that it's constant. So this is a simple way to write those three assumptions, and then linearity is kind of your baseline, most obvious assumption in regression. We're fitting lines. So I hope that this discussion and this mnemonic helps you to remember those assumptions. One other assumption I want to mention that's not really related to your model, but related to how you select for your variables is multicollinearity, which is a big word, but if you break it down by the prefix and the root, really just means you don't want your variables to be correlated. And the reason for that, as we alluded to in past lectures, is it waters down the effect of the variables, because the interpretation of the coefficient or the effect of each variable is it's the change it causes to the response for every 1 unit change in the independent variable, holding all other variables constant. So if your variables are correlated, the order in which they go into your model is going to affect their effect, the size of their effect. So just to give you a quick example, kind of like we did in the previous lecture, we were predicting weight. So let's say we're predicting weight again, and we know height is something that affects weight, so does calorie intake, right? So if we were to regress height on weight, if we were to regress it in the order height first and then calorie intake, height is going to capture most of the variation that affects weight, whereas calorie intake is going to kind of absorb leftover variation that wasn't captured by height. And that hurts your interpretation, because if you want to know the effective calorie intake, it's now being watered down by some of the variation captured by height, assuming that height and calorie intake are somewhat related, which is, I think, is a reasonable assumption in this example. Another problem with this that doesn't have to do with multicollinearity in particular is that the more variables you add to your model, the more variation you're necessarily explaining, because that's the nature of least squares. If you were to do out all the calculus, right, the more variables you add, you're explaining some variation that might not be attributed to that variable. So in other words, your R squared statistic is always going to go up. You're always going to improve the percentage of variation being explained by the model, even for variables that are actually not significant or not contributing meaningfully to the model. And there are other criteria that fix for this that you'll learn about in future classes. But when you put a variable that's highly correlated with existing independent variables in your model, not only are you creating an interpretation for that variable that's harmful, but you're making the model appear more powerful than it actually is, which goes back to the examples we've done in the past. And that's why I told you remove variables that are not significant. So yeah, you don't want to ruin the interpretation, but the other reason I told you to do that is you don't want the model to appear better at predicting than it is, because you could throw variables that are totally unrelated on there and it's going to improve the prediction marginally, even though those variables aren't meaningful. All right, so that was a lot on multicollinearity. These are the assumptions I want you to focus on. These are the most common ones that are related to the model, but I do want you to be aware of multicollinearity when you perform variable selection for your model. And you can avoid this by looking at the significance of the coefficients on your variables and switching around the order of your variables and seeing how much that changes their significance. You could also do this by looking at correlation within your variables. So in the former approach, switching the order, variables that were previously insignificant because they appear later in your list of independent variables, or regressors is another way to refer to them, and that's how I'm going to refer to them now. Variables that appear later in the list of your regressors are less likely to be significant if they're correlated with regressors that appeared earlier in your model. And when you reverse the order, if they become significant, they're very likely correlated. But that's a really roundabout way of checking for multicollinearity. The best thing to do is to just compute correlation among your variables, if they're numeric. If they're not numeric, there are other tools we've talked about to address this issue of multicollinearity. There's ANOVA for a categorical and numeric variable, and in the event that you have two categorical variables, you could do a chi-squared test. So yeah, I do want you to be aware of that, even though it's not really an assumption of your model. It's more of an assumption in terms of how you do variable selection. So let's go over how you check for each of these things. So this is the pattern I was referring to before where linearity is violated, and I want you to look at this graphic right here. So ignore the lines for a second, and it looks like there's some positive correlation here. And in fact, you can see that, like, the red line does a good job of explaining the data, but the blue line does a better job because this data isn't quite linear, it's actually quadratic. And as I mentioned, there's a fix for this in called transformations that we're not going to cover in this class, but more advanced classes we'll go over. And I just want you to, looking at this, notice that these residuals are all positive and over the line, with the exception of a few here that are under. So in this range, you're getting mostly positive, larger residuals. In this range, you're getting exclusively negative. Right? In this range, you're getting almost exclusively negative with the exception of one. And that results in this pattern in the residual plot. So this can be a little hard to see here. And these are two different graphics that I got from two different websites, so they don't correspond exactly one-to-one. But I just want you to look at this and say here, it's not super obvious that we should be using a quadratic transformation instead of linear regression, or in addition to linear regression, I should say. But when you look at your residual plot, it's very obvious, right? It's no longer evenly distributed around zero. There's a clear pattern in the residuals. Linearity has been violated, constant variance has been violated, independence has been violated, right? All of those assumptions have been violated. And you could even argue that normality has been violated too, because if it's normal, the center is changing, right? Here it's like normally centered at a lower value than it is over here. So this is just like a clear indication that something's wrong. And as I mentioned, the fix for it is transformations, which you'll learn about in the future if you continue to study statistics. Now let's talk about independence and checking for independence and constant variance. So this is kind of a similar issue. Here you see a chart that looks pretty good. And some of you may say, well, it looks a little bit football shaped, right? And the variance is a little higher in the middle. There is going to be some variation, and it does take practice to get good at this, but you're never going to see, or you're rarely going to see, a residual plot that's perfectly even throughout. And this is pretty roughly even. Also notice you have less data points at the extremes, right? We only have 3 here. And with a normal distribution, we know we're more likely to see things in the center. Whereas here you have like a dozen or so data points. So we do get a majority in the same range as those 3, but then you get some extreme values on occasion. So even though it is somewhat football shaped, accounting for the fact that there are fewer variables at the extremes of the fitted values, this is a pretty good representation of normality, constant variance, and independence. I'm missing one. Normality. Linearity I forgot to talk about. Yeah, and linearity is the absence of the pattern. But we're talking about these two right now, independence and constant variance. So this is a good example of like what you want to see in your residual plot. And these are examples that are problematic. So in this example, there's a clear pattern, right? We start out with positive, then we get some mixed residuals, then we get a bunch of negative residuals. And that's largely due to this outlier right here. And residual plots can be helpful in diagnosing what is going wrong in your model. And if you were to remove this outlier, you'd very likely end up with a valid model that looked more like this. Because this outlier is hugely influential, which we didn't talk about, but you did see in the output of JUMP, there were some plots diagnosing the influence of certain points. And removing them can be helpful, although there's a trade-off there in that if it's a valid data point, right, you're losing information that could be helpful in predicting your model. So it's not as simple as let's just remove problematic data. There's a cost to that. And here we have a phenomenon called heteroscedasticity. So this is homoscedastic, meaning that the variance is consistent. That's what that prefix homo means throughout the graphic, whereas here you see the variance is clearly changing. It is not constant, it is not equal throughout the range, and this is also problematic because you're predicting really well over here and then your predictions get worse and worse here. And this is not due to having less data points because there's many data points over here. There are more over here, but like even within this range we see like the variance increasing for roughly the same number of data points. So this kind of shape is also problematic and indicative of the need of a transformation, which again, we're not going to talk about in this class. But you should know if you see something like this, your model is invalid, and you should not report on it because the results will not be reproducible. Okay, so that's mostly about checking for the bulk of the assumptions. I want to talk a little bit about checking for normality, even though this is more nuanced. So I do think you can kind of assess normality from a residual plot, but probably the best plot to use is known as a QQ plot, which is what you see over here. But before getting into QQ plot, I wanted to talk about the histogram. Like you could just make a histogram of your residuals, and you know the normal curve is bell-shaped as you see it superimposed over the histogram. And you know it's not going to be perfect because there's random variation, but this is roughly bell-shaped and it looks good. The QQ plot, on the other hand, and it doesn't have to be just for the normal distribution, but that's the common example when you're checking your residuals, is you plot the theoretical, well, we don't have to get into the technical details of it, but it's essentially comparing the values you observed versus the values you would see in a normal distribution, kind of like our predicted versus actual observations. You want it to lie along the straight line y equals x, and there's going to be variation, and sometimes you'll see it pull off slightly, like over here it pulls to the right, Over here, it's actually behaving pretty well. But these slight variations are not cause for concern. You just want to see it roughly lie along the line. I know it's a little subjective, and there are other tests you could perform that are more objective at testing these assumptions, but again, I wanted to keep this light because we are covering a ton of material in these last 3 lectures. So this is one way to check for normality. I think if all you do is look at a residual plot in your project, you're good to go. I just wanted to make you aware of these other approaches. So that's mostly about checking the residuals related to your model, which we learned with the acronym LINE, which stands for linearity, independence, normality, and equal variance. Now let's talk about multicollinearity. As a refresher, we kind of already had the spoiler on this. Does the order of the variables in your model change your estimates and the significance of those estimates? That's a clear sign of multicollinearity, but it's a roundabout way of measuring it. A more proactive and effective way to measure it, or I shouldn't say effective, but definitely more proactive way to measure it, is to just look at the correlation between your independent variables. And again, if they're categorical, you can't use correlation, but you can use ANOVA or chi-squared as appropriate. ANOVA in the case where one is quantitative and the other is categorical, and chi-squared when they're both categorical. And those will both give you indications of multicollinearity. Okay, so that's a lot about checking for assumptions. This is really important. Do not skip this if you did linear regression. You don't want to build a model that's inaccurate and share results that are invalid. Lastly, thank you. It was really nice to have all of you in class. A lot of you attended office hours or reached out over email. It was great to work on it with you one-on-one. You're a very dedicated, hardworking group, and it was really a pleasure to work with you. And I'm looking forward to going over your final projects. I will give very detailed feedback, even though I anticipate you'll all get a good grade on them. I want to make sure you have the feedback to grow in those guiding principles when it comes to writing research of simplicity and clarity and applying what we learned in this class, EDA, statistical inference, and so on. So please do review those reports even after you get your final grade. Which I'm sure you'll be happy with, but I do want you to take the time to absorb that feedback and improve. So thank you again, and enjoy the fall semester.